Hi, my name is Paige Bright, and I'm excited today to be presenting for Happy's Hello World series. And today I'll be talking about a continuum Erdos-Beck theorem, which is joint work with Caleb Marshall. And the problem that we'll be talking about today is precisely described in the picture below, which is if I give you a bunch of red points in Euclidean space, we want to be able to count how many lines are there that contain at least two of those given points. And this is what we'll be talking about today, both in the discrete setting, which is classically studied, as well as the continuum, which has been in recent development. So let's restate the problem with some notation. So we take a subset X and Rn, and we consider the set L of X, which is a set of all lines in the affine Grassmannian, i.e. AN1, where the set intersected with the line is at least 2, i.e. every line contains at least 2 points. And I'm going to refer to this as the line spanned by the set. And the question is, given your set X is large in terms of cardinality or in terms of Hausdorff dimension, and it satisfies certain properties that we'll talk about momentarily, we want to know how large the set of lines spanned by X is. The continuum versions of these problems were recently studied by Orpin, Schmerken, and Wang, which I'll commonly abbreviate to OSW, Kevin Wren, and myself and Caleb Marshall. And most of the tools have been involving radial projections and dual Furstenberg set estimates. So I hope to motivate these two tools, both in the proof methods described throughout this presentation, as well as some open problems near the end. All right, a bit about me before we get too deep into it. I just finished my undergrad last semester at MIT, working with other graduate students of Larry Goose, including Alex Ortiz, Xiangwen Gan, and Yucho Fu. This next year, I'll be at UBC working on my master's under Isabella Laba, Pablo Schmerken, and Josh Saul. And then I hope to return to MIT and get my Ph.D. under Larry Goose. At least that's the tentative plan. I started getting into research in 2022 with Xiangwen Gan, studying exceptional set estimates for radial projections. This is how I sort of got into this area in the first place. And then about a month or two later, Orpin, Schmerken, and Wang came out with Kaufman and Falconer estimates for radial projections and a continuum Beck's theorem. And I think this result is very cool. The tools that go into it are very neat. So much so that the next year, in 2023, I worked on UPenn Study Guide Workshop, studying OSW a little bit more closely and writing a study guide on it with myself, Ryan Bushling, Caleb Marshall, and Alex Ortiz. And through this workshop, a number of questions arose naturally, one of which involved my work with Caleb Marshall, which is what I'm talking about today, a continuum Erdos-Beck theorem. All right, so let's state what Beck's theorem is. If you have a subset X and Rn that's finite, let's say it has n many points, and we're going to suppose that if I take away any line from my set, it still has a large amount of the points, i.e. no line contains too much mass. And this is going to be true for every single line. Then the set of lines spanned by X is approximately n squared, which is heuristically what we should expect. Because if X doesn't give too much mass to any particular line, i.e. it's somewhat random, then we should hope that X will span about n choose 2 or n squared many lines. The proof of Beck's theorem follows from an application of similarity Trotter for k-rich lines, and this is available on the Wikipedia. I think the proof is very elegant, and it's very interesting to see how these two are related, but for our purposes, we'll just leave it there for now. So just some key examples that I'll be revisiting over and over again in today's talk. That I like to keep in mind is if your set is completely contained in a line, then the set of lines spanned by X is exactly equal to 1. It's very small. But as soon as you start removing points from this line, like in this example where there's only 1 point off the line, then we start getting more lines, all things told. I.e. here we have X many lines, 1 from the ones on this line, and then 1 each from the other 2, from all the other pairs. But the further and further we get from being completely concentrated on the line, i.e. here where at most half of the points are on any given line, then the set of lines spanned by X is approximately more like n squared. And as you can imagine, this becomes more and more true as you have closer and closer to like 1,000,000 lines as opposed to 6. I just wasn't going to draw more here. So the continuum Erdos-Beck theorem that Orpin, Schmerken, and Wang proved in 2022 states the following. If we take a subset X and R to Borel, and if the dimension of X minus any line is equal to dim X, then the dimension of the set of lines spanned by X is at least a minimum of 2 dim X and 2. Let's unpack this a little bit. Here, when I refer to dimension, I'm referring to Hausdorff dimension, like the fractal dimension of a set. One thing I'll note here is that Hausdorff dimension on this side of things is denoted in terms of Euclidean space, i.e. we're looking at the dimension of the set of points in R2. Whereas here, when we're looking at the line spanned by X, we're literally looking at the subset of lines in the affine Grassmannian. So these are in fact different metric spaces, which is very interesting, I think. Secondly, this lower bound of 2 is in some sense a trivial lower bound. The set of all lines in 2 dimensions is 2-dimensional as a subset of the affine Grassmannian. So therefore, the set of lines spanned by X should be at most 2-dimensional. So as soon as dimension of X is larger than 1, we divert to the trivial bound. And lastly, a question that I think is very interesting to think about is why is this 2 dim x the continuum version of Beck's theorem? Well, the way that it was explained to me by Alex Ortiz, at least heuristically, is this idea that if I have initially n squared many lines in the discrete setting, then we should expect the logarithm of that result. 2 times log n will replace log n with dimension of x. And heuristically, this is why that works. Heuristically, if we cover x by delta balls, where delta is very small, it should heuristically take about delta to the minus dim x many delta balls. And let's call that n. This is not completely true, but this is at least a heuristic. And then the idea is that if we cover the set of lines spanned by x by delta balls, it should be still approximately the number of delta balls it took to cover x choose 2, which is n choose 2, which is approximately delta to the minus 2 dim x. So by the same heuristic reasoning that implies this approximate equality, we'll end up getting that the dimension of the set of lines spanned by x is at least 2 dimension of x. This, of course, is extremely heuristic. The tools that actually go into the proof are more difficult to actually get across. But this is how I like to think about the idea of how we go from a discrete problem to a continuum one, at least in terms of conjecturing problems. So let's talk about how the proof of Orphan, Schmerken, and Wong's result works. Initially, we can always write that the set of all lines spanned by x is a union of lines through individual points in your set x, i.e. we're going to write as a union of points x and x, and the set of lines that pass through x that are contained in my line spanned by x. No, it's quite a mouthful, but the idea is that we're just decomposing my set of all possible lines into lines through specific points. And the idea is that using radial projections, we can show that the set of lines through any particular point is often quite large for many of the points in x. So let's see how this works. Firstly, let's define radial projections. If we give you 2 points x and y in Euclidean space with x not equal to y, then we can define the radial projection pi x of y to be y minus x over the size of y minus x. Intuitively, this is the point on the sphere around x in the direction of y. So here's y, and here's the radial projection of y onto the sphere about x. And you can think about it as just being the unit sphere. And the idea about how these are related to the set of lines that we're considering is the following. If I have my point x here and I look at the radial projection of my big set capital X onto the sphere about x, then this is going to correspond to lines through little x with at least one other point in my set based off of the pre-image. In fact, one can check carefully, as Caleb and I do in our paper, that you can identify a set of points on the sphere with a set of lines that pass through those points on the sphere in the Grassmannian around it. And so, in fact, the dimension of the set of the radial projection is equal to the dimension of the set of lines for that point. So the question of how often is the set of lines through a particular point large is roughly the same as asking how often is the radial projection large, and similarly, how often is the radial projection small? And this is the question we'll be exploring around today. So let's revisit our key examples to see why this is a good idea. So the question then becomes how often, and how large can the radial projection be? And in our key examples, the thing of note is that if you're completely contained on a line, then the radial projection is always going to be quite small. It's approximately 1. But as we start taking points off of the line, see here we just have 1 point off of the line, then we at least have some point where the radial projection is quite large, i.e. it's about that. But the further and further we get from being not contained in the line at all, at least not contributing a large mass to any particular line, the closer we are to having more points x through which the radial projection is quite large. And this is heuristically what we should expect in general, and this is what the result of Orphan, Schmerken, and Wong shows. Their result on radial projection show the following. You can think about x and y here being in the plane R2, but as we'll talk about later, this was generalized to Rn by Kevin Wren. So if I have a set x that's contained in the plane that's not contained in a line, then the supremum of x in x, the dimension of the radial projection of y onto little x, is at least the minimum of dim x, dim y, and 1. Now let's unpack this a little bit. If we're in the plane, then radial projection corresponds to projecting onto a circle, so the dimension of the radial projection should be at most 1. So in that sense, the radial projection here is also, or the bound of 1 here is also a trivial bound. In the same way, if you start by projecting a dim y-dimensional set onto a circle, it should still be at most dim y-dimensional. It shouldn't project to something larger than it initially was. So this dim y term here is also in some sense a trivial lower bound. The real thing that's improving is the fact that if we have a larger set x, i.e. a set of larger Hausdorff dimension, then we should be able to find more and more points with larger radial projection. That's the intuitive way I like to think about this theorem, which is of course true. And we'll use this for our advantage of showing that the set of lines for a particular point is quite large. Or in general, the ones where it's quite small doesn't happen that often. So let's do that. Let's let sigma be between 0 and the minimum of dim x and 1, which is like we're ignoring this dim y term, but with y equal to x. And we're going to let B be our set of bad points, the points x and x, with the dimension of the rate of projection is strictly smaller than sigma. And the claim is that the dimension of x minus b is in fact equal to the dimension of x. To prove this, we'll suppose otherwise. Let's suppose that the dimension of x is strictly bigger than the dimension of x minus b. If this occurs, then it also follows that the dimension of b equals the dimension of x, which will be important shortly. But to apply our theorem with x equal to b, the idea will then have to break it down into cases of whether b is contained in a line or not. If b is not contained in a line, then the theorem states that the supremum over points in B of the dimension of the rate of projection is at least the minimum of dim x, dim b, and 1, but we know that dimension of B is equal to dim x by assumption, and so we get that it's equal to the minimum of dim x and 1. But by assumption, this is strictly bigger than sigma. That's how we define sigma. And our set B is defined such that the rate of projection is strictly smaller than sigma. So this is a contradiction. This first case can never happen. But if B is contained in a line, then we can just create a string of inequalities. The dimension of x is strictly bigger than the dimension of x minus b by assumption, which is of course bigger than or equal to the dimension of x minus the line that b is contained in. But in Beck's theorem, the continuum Beck's theorem, we're supposing that x gives no large amount of mass to any particular line. So this is equal to the dimension of x by assumption. And so this is also a contradiction because we get the dimension of x is strictly bigger than the dimension of x. And that can't happen. So in the end, we conclude that the dimension of x minus b is equal to the dimension of x, and for every point x in x minus b, the dimension of the rate of projection is quite large. It's larger than or equal to sigma, which I'll remind all is equal to the dimension of L of x, the set of lines through the particular point x. Now let's use this to our advantage, because at this point, what we've shown is that our set of lines spanned by x contains a union of large bushes, i.e., it contains these line families L sub x, which are lines that pass through little x, and by assumption, they're all at least sigma dimensional. And we also have a sigma dimensional at least set of points x in our union, that we're taking the union over. And as it turns out, these types of sets have been studied quite a bit. 2 dimensions or Punishmark and Wong didn't need this result. We'll talk about why that is momentarily. But here's the following general result that holds in Rn that will be helpful for later, which is due to myself, Yuchofu, and Kevin Ren from earlier this year. It says that the dimension of a union over a t-dimensional set of points x, where through each point x, there's at least an s-dimensional family of lines for that point. The dimension of the union of these lines is at least s plus the minimum of s and t. This is known as the dual Furstenberg set. We'll get to it more momentarily, but for now, we'll just use this result here. Right now, we have s and t being at least sigma, so therefore we have the dimension of the set of lines spanned by x is at least 2 sigma. Setting sigma to be as large as possible, i.e. the minimum of dim x and 1, proves the entire result. All right, so let's talk a little bit more about these Furstenberg sets. In particular, we'll start with just a regular Furstenberg set, which is the following. We have a set x in Rn and a set of lines in the affine Grassmannian, such that the dimension of the set of lines in the affine Grassmannian is at least t, and the dimension of x intersection with any line is at least s for every single line in my line family. And the question is how large is the dimension of x? We would hope that in general that because each line contains many points, and we have many lines, that this would be quite large, but checking this is quite difficult and is known as the Furstenberg set problem, which was recently resolved last year by Kevin Ren and Hong Wang. But we can ask a very similar question about what are known as dual Furstenberg sets, where here we have a set of lines in the affine Grassmannian, a subset x and Rn, such that the dimension of the set of points in Rn is at least t, and also the dimension of the set of lines through a particular point x contained in my line family is at least s for all x and x. And then the question is how large is the dimension of the set of lines, i.e. how large is the dimension of the union of the lines L sub x? That's the same sort of thing here. If we know we have many pins and we know we have many lines through each pin, then we should hope that the dimension of the set of lines as a union is quite large. The issue is that some of these lines can overlap between 2 points as is seen in this diagram. Now you may be wondering why this is called a dual Furstenberg set. As it turns out, they're in fact precisely dual in 2 dimensions. The idea is you can identify a line, y equals mx plus b, in the Furstenberg set case with the point, or vice versa, with the point m comma b in the plane. And this point line duality is what allows one to go from Furstenberg sets, which are more classically studied, to dual Furstenberg sets, which have been of study most recently, though both are interesting questions, of course. So this is why in 2 dimensions, Orphan, Schmerken, and Wong didn't need to use dual Furstenberg set results of myself, Yuchofu, and Kevin Ren. They instead could just appeal to Furstenberg set estimates in the plane. That said, in higher dimensions, this duality doesn't quite hold. I personally feel like dual Furstenberg sets should be referred to as pinned Furstenberg sets, but this is neither here nor there. In higher dimensions, we have hyperplane duality, but not with regards to lines. Let's just continue on for now. The last thing I'll note is that we can also study line sets in Rn, not just in the plane. There's a result of Kevin Renz from 2023, which states the following rate of projection result, which is that if X is not contained in the K-plane and is contained in Rn, then the supremum of the dimension of the rate of projection of Y onto X is at least the minimum of dim X, dim Y, and K, which is precisely the same sort of setup as we had before when K was equal to 1, i.e. X wasn't contained in a line. Using this result and the result of myself, Yu Fu, and Kevin Ren, we can get the following corollary, which is like a continuum version of Beck's theorem in higher dimensions. We take a subset of Rn such that the dimension of X minus any K-plane is equal to dim X. Then the dimension of the set of lines spanned by X is at least the minimum of 2 dim X and 2K. Here I commonly think about K being equal to n minus 1, because the dimension of the set of lines contained in the Grassmannian is at most 2 times n minus 1. So in other words, this is in some sense also kind of a trivial bound, though it becomes more precise because K can be anything between 1 and n minus 1. But this 2 dim X here is precisely the analog one should expect from the discrete version of Beck's theorem. There's also a more general version of Beck's theorem, which was proven shortly thereafter. That was the focus of myself and Caleb Marshall's work, known as the Erdos-Beck theorem. And it states the following. We could take a subset X and Rn finite, let's say it has n many points. Now, as opposed to assuming that it doesn't drop too much if we take away any line, we're going to assume that I take away any line from X, that it at most drops down to T for all lines L in the affine Grassmannian. Then the set of lines spanned by X is at least NT. This is very similar to what we had in the first place, which T was equal to N, right? X minus any line is at least N, then we should have N squared many lines, but this is in some sense more quantitative. In other words, if X does not give too much mass to any particular line, then it'll span NT lines in this particular setup. And so during the UPenn Study Guide workshop, Caleb, Marshall, and I, as well as our teammates, noticed that there was this more general version of the Erdos-Beck theorem. And we asked the question, is there a continuum analog of this result too? Right? We have this discrete result from combinatorial geometry, and we want to know if it's going to hold in geometric measure theory. And the result of myself and Caleb Marshall says that, in fact, this is the case. So let's talk about how that works. The result is the following. It could take a subset X and Rn that's Borel, and we fix some K between 1 and n minus 1. Then we have two cases. The first case is the result of Kevin Renz, though we still state it to show the dichotomy, which is that if the dimension of X minus a K-plane is equal to dim X for every K-plane, then the dimension of the set of lines spanned by X is at least the minimum of 2 dim X and 2K. This is the result we talked about earlier. But if this is not the case, if the dimension of X minus any K-plane is not equal to the dimension of X, then it must drop for some K-plane. So we're going to let T be between 0 and dimension of X, such that the dimension of X minus this any K-plane is at least T. So in other words, we're allowing it to drop, but at most drop down to T. Then the dimension of the set of lines spanned by X is at least the dimension of X plus T. And again, I should note this is the analog one should conjecture. It's like the logarithm of n times T, except to replace log n by dimension of X. So this discrete to continuum analog is continuing to hold up, at least heuristically. Now let's talk about the proof outline of the result with myself and Caleb Marshall. The idea is that now we have a K-plane that contains a lot of points. That's our assumption. So we need to use that to our advantage. In particular, we know that the dimension of X minus this K-plane is less than dimension of X, which tells us that X intersection of this K-plane must be quite large. It's dim X dimensional. Not only that, we also know that for every X that's not contained in this K-plane, that the dimension of the rate of projection of this K-plane onto the sphere around X is as large as it can be. It's a Lipschitz map locally. So therefore, the dimension of the rate of projection is equal to the dimension of the set of lines through a point X, which is at least and therefore equal to the dimension of X. We elaborate on why this holds beyond the heuristic outline here in our paper, but for now we'll just use it. And in particular, we found that our set of lines spanned by X contains this union over pins that are at least T-dimensional, through which each pin, there's a set of dim X dimensional lines through each point. And so therefore, using the result of myself, Yu Fu, and Kevin Ren, we're able to obtain that the dimension of the set of lines spanned by X is at least dim X plus T, since T is strictly smaller than dim X, so that term doesn't matter here. This is the rough proof outline of what we did, but I find it very fascinating the fact that we were able to conjecture this result and conjecture different tools that we would need to get this result purely based off of the discrete geometric examples. So let's talk about some further directions this research can go in. Firstly, today we talked about dual Furstenberg sets of lines, or as I think they should be called, pan-Furstenberg sets of lines. But I think in higher dimensions, it'd be interesting to study unions of K-planes through pins. This was recently studied by work of Li and Liu, but I would think it should be explored further. And I think it's possible to make conjectures on what bounds we should expect based off of these discrete geometric problems. I also think it'd be interesting to study more general versions of radial projections. Here we identified the radial projection about a sphere through the set of lines for a particular point. I think it would, in general, be interesting to see what would happen if we considered sets of planes through points, where in particular we take a subset of points in Rn and we map it to the set of planes that contain at least 2 points in those subsets around a specific point. I think that would be interesting to understand more deeply, though would require much more machinery, I'm certain. I also am interested if there are more examples of results from the discrete problems to the continuum problems or vice versa. There's some upcoming work of myself, Alex Ortiz and Dima Zakharov, that talks about this back and forth a little bit more, at least for a different type of problem. And lastly, in the result of myself and Caleb Marshall, we also conjecture what line sets of product sets should look like. In particular, we think that there's a more general version that would imply the result of me and Caleb Marshall under some assumptions. I won't go into the details here more. It's contained in our paper. Thank you very much for listening, and I'm glad I got to give this talk, so thank you very much.